how to pronounce it before.
That was good.
Okay. Can you hear me? So yeah, I'm Jalo Nousiainen. Where's the pointer? Oh, here. So I'm a postdoc at ISO. I'm going to talk about reinforcement learning control for wavefront control. It's a joint work with a bunch of people. We have our small group at ISO. We collaborated with a team from LAM for on-sky testing, and we're working on focal plane wavefront control with the team from Liège. So yeah, we want to image exoplanets. So what could go wrong? Maybe we have a strong wind, and we end up with this wind-driven halo. That's bad. Maybe we don't have a wind. We end up with low wind effect. That's bad. Or maybe like everything works just fine, but we are still limited by the known common path errors. So what I try to do is solve these problems with algorithms. So no hardware. So yeah, today I'm going to talk about like a few things. Wavefront control with adaptive optics with PO4AO, and on-sky testing with that, and then focal plane wavefront control with similar ideas. So yeah, this is the basic AO control loop here. So we have a wavefront, DM, beam splitter to the science arm, and then the wavefront sensor. And typically this is controlled with integrator control, which is nice and robust for many applications. But when we push the contrast down, we start to see these error terms. Most prominently, we see this time delay and the photon noise projected to the deformable mirror. And we can address this with predictive control. But these additional like real-world error terms makes it a bit tricky many times. So we have non-linearities in the system. We might have a misregistration between the deformable mirror and the wavefront sensor, maybe something else. So what if we replace this controller with robot? So this small machine learner here. So this machine learner here, it reads the telemetry data. That's the wavefront sensor measurements, the deformable mirror commands, and we allow it to give commands to the deformable mirror. We give a reward function for this robot, so that's the objective. We tell it to keep the wavefront flat, and now it tries to figure out how to do it. So the specific algorithm that we use is called policy optimization for AO. If you want to read about it, there's an article published at ANA. So it uses the two neural networks. So we have the dynamics model. So that's kind of like the digital twin of your optical path, learned from the data with neural networks. And then we have a policy neural network. That's basically the controller. And both of these models are like trained online all the time. So they adapt as we control the system. So I used this term reinforcement learning, but we're basically doing just online system identification plus some form of model predictive control. But when we do it with neural networks and all the differentiation, we can use the term reinforcement learning. So yeah, so it worked really well in simulations. So then we tried it in the lab. So COAST is our XAO test bench at ISO. So yeah, we implemented it there and we run it. So we have like super low latency system, and our like speed limit is determined by the SLM that we use for the turbulence, so we don't really have delay in the system. So we added delay here, and if you look at the integrator, when we start to add the delay, you can start to see the wind-driven halo. That's ruining the contrast. And for PO4AO, I mean, we don't see it because it predicts the wavefronts. And on top of that, we did an experiment where we started to shift the deformable mirror off axis while we were controlling. So if you look at the blue line here, that's the integrator. So first you see that this loss of performance gain here, and then it becomes unstable. But as we learned the system from like online system identification, PO4AO is not really bothered by it. And also, if you have some vibrations, we can bring them down with PO4AO. So for example, here we have this vibration in our bench, and we can bring it down with PO4AO. So that's great. So does it work on Sky? So yeah, we implemented it on Sky to PAPYRUS AO system. It's on a 5.5 meter telescope at OHB, southern France, challenging seeing conditions. So yeah, so we did this experiment last summer. So here's some PSFs from the night. So here I picked for PO4AO and for the integrator the best PSFs that we get during the night. And if we run the video, we can see that PO4AO is much more stable. And you can also see it in the stray ratios. So we almost gain a factor of 2 for these cases. For these PSFs, we have this astigmatism because we didn't correct the NCPA errors while we were running. And it's completely turnkey operation, so I didn't tune the algorithm at all. We just push the button and it's on. So here's all the PSF data that I collected that night. So the orange is PO4AO, and then we have the integrator. So it's quite a big difference. But a bit of a disclaimer, we had a strong wind, bad seeing, and we were not like super careful with the integrator gain. So to conclude this part of the talk, PO4AO, I mean, it's a turnkey operation. You don't need to know how to use it. You just push the button and it's on. It's adaptive to changing conditions, star magnitude, missed registration, vibrations, also on Sky. I have some additional slides. We can talk about it after the talk. Really consistent results on bench, on Sky, in simulations. What we still need to work on is the implementation. So this time we implement it with Python. And I mean, the latency was kind of okay, but we had really big jitter. That's because we only had one GPU, so we had to train on the same GPU as we control. And we had like huge frame skipping, which I think makes it even more impressive, the results. So to continue, I mean, that was AO control, but really what we care about is the PSF, because that's where we do our science. So what if we use the focal plane image to do control? So as we know, focal plane is a bit more difficult. For example, we have this problem with the phase ambiguity. And the idea is here that if we collect the data from past, maybe we can solve for these ambiguities and control the deformable mirror from that data. This usually goes in like under a term sequential phase diversity, or like fast and furious type of algorithms. And here we have to modify the reward function a bit. For example, with corner graph, that might be just minimize the flux in the image. And the action then would be on separate NCPA DM, or maybe offsetting the AO control loop. So because it's a bit more difficult problem, we need a robot update, more processing power here. There was a poster about it. So yeah, so this is the name of the game. So we have a static NCPI pattern. We give this robot 20 steps to correct for it. And let's go. And it digs this nice dark hole here. Really, the phase errors go down to the level of fitting error here. So we did this for 500 different NCPA errors to get some statistics how it behaves. So here we compared to the open loop case, so no correction. And then if we project the phase to the deformable mirror, and this is the PO for NCPA. So what's interesting here, I think, is that we have this here where the fitting error is below the PO for NCPA, and you might think, okay, that's not good. It's not working perfectly. But here the reward function was actually the whole flux in the image, and then when I combined the whole flux outside the control region, it was actually better than the fitting error. So with that respect, it was working pretty optimally. So a nice application for this is the water vapor seeing. So in this case, we would have really dynamic NCPA errors. So we can use it for that off the box. And now it tries to kill the speckles as they appear there. And we can do the same exercise here. Look at the long exposure PSF. So I want you to focus on this image here. So again, we have the open loop. We have the PO for NCPA, but this time I added this reference controller. So this is the fitting error plus time delay. So this is actually like perfect phase reconstruction combined with one-step delay integrator gain. So this would be kind of the performance that you would get with optimal AO system for correcting these phase errors. And from this image, you can see that our method is like actually performing as well as the best possible AO system. So that means you can actually run it as fast as adaptive optics system. So up to like several kilohertz. So how does it work? I mean, from this image, we think it's like introducing every second step some phase diversity because the NCPA error is constantly changing, so it needs to solve for that. Yeah, so we are model free. We can apply it to standard imaging or for the ELT pupil. So that would be the list here. So we have the ELT pupil, vector vortex corner graph, background noise, everything, or standard imaging for PSF sharpening. And same for the reward function. I mean, we can dig dark holes. That would be the vector vortex corner graph, or with perfect corner graph. Yeah, and then to conclude, it's a model-free method. It works for every aperture, every corner graph. We don't need really flat reference. PSF sharpening, phase correction, dark hole digging. You can use it as an adaptive optics system. At the moment, we are limited to like 100 modes with the method that we have. It has this kind of embedded decision making, what we call like you have to figure out how to get phase diversity to solve for the phase errors to correct. So balance between phase diversity and performance. It's adaptive to changing conditions, so you can train it online. And now for the future work, I mean, bit more in-depth simulations, lab tests, small modifications to the algorithm to make it usable for more degrees of freedom. So with that, I'd like to thank you.
Oh, thanks. It's really nice talk. I have a question. Do you think it's really necessary to use deep neural networks to learn your control policy? Because if we think about like the PAPYRUS probing and EFC, actually we can define a purely linear quadratic control policy and it can still do a pretty good job. So, but I'm thinking if you use deep neural networks, first it has to use a lot of power using GPU, and then it can also be slow if you want to do really fast, like several kilohertz. So can you comment on this part?
Yeah, I mean, for AO control, for some reason, neural network seems to work better, especially when you have nonlinear wavefront sensing. For the focal plane stuff, I haven't tried yet, but yeah, you could replace the neural network policy with matrix or linear model. Yeah, maybe I try it at some point. But it depends on like how close you are to the linear range.
Okay, last question.
Could you say a bit about how you assessed loop stability, either in the simulations or lab or on Sky? How did you make sure that it wasn't, blowing up the control loop? Because there's, in sort of classical control, there's these, you can set phase and gain margins, and you can't really do that here. So is there some equivalent?
Sorry,
For assessing loop stability, if you have an integrator, you have like margins that you can set to make sure that your control loop will stay stable against any aberration. Is there some equivalent in the reinforcement learning case?
Like you mean like theoretical limits for stability.
Or anything empirical either.
We just, try things, and it seems to be like really stable. And most of the time, I mean, it's more stable than the integrator in the lab log. For example, we can run like Zernike sensor beyond the linear range, where the integrator is like super unstable. With this algorithm, we can make it much more stable.
All right, thank you.
All right, let's thank Jalo again.